So
Uh-huh.
I can kind of, build experience there and then come.
Oh, I see, I see.
I guess I have that advantage.
Like home means Kuwait, you mean, or?
Yeah.
I see.
So yeah, I can probably work there for a few years.
Oh, okay.
Maybe work on publishing things on there and then
Oh, I see.
come apply here.
Oh, that's cool. I mean, you mean academia is not very competitive there? I mean, in terms of getting jobs?
No, honestly, like, I'm not exaggerating, but I might, me personally, like learning all this stuff, if I go back home, I might be one of like the top political science people because no one does quantitative methods at all. Like when I was learning there, the introduction to political science was like a 70s textbook.
Yeah, right.
So it's not that competitive.
No, absolutely. You might be a very important person in the evolution of political science in Kuwait.
I hope so.
Yeah.
I mean, that's genuine, I hope so.
Yeah.
I'm trying to learn all of this because I want to teach it.
Right.
I want to teach methods.
Right, of course.
Because I feel like I can do on my own time, work on the things that I'm interested in.
Right.
But where I can really benefit is by teaching the students methods because no one teaches methods.
Oh, interesting.
So everyone just, I don't know what they teach.
Right. My dad was a little bit like that. Like, he was one of the, and my mom too, but my dad was one of the first people in Korea to get a PhD in math in the United States. And his teachers in Korea got their PhDs in Japan, for example. So he was one of the first Korean ones. So he got a job at UC Berkeley. He thought about going back to Korea, but then he decided to stay at University of Alabama. And so he had some students at the University of Alabama, and those students who are now, they're all, retired, but they were among the first Korean mathematicians to be trained in the United States after him. So, if you're the first person, you can really make a big difference, seriously. And so,
I feel like here it's just, if you're looking at everything here, it feels like everything's fully developed. The
Right.
field is really not only fully developed, it's developing beyond anything we've ever seen.
Right.
There's so many methods. Everyone's competing the market here is just really, really, really amazing for
Right.
universities.
Right.
But in other parts of the world, I mean, Europe, I feel like it's similar to the US, maybe
Right.
less competitive.
Yeah, right.
But in Africa and
Right.
East Asia.
Right.
Asia, I think, is a bit more competitive, but Middle East,
Yeah.
Africa, I think, is definitely the least competitive.
Yeah.
Maybe Latin America.
Yeah, exactly. Yeah, so, you can make a big difference. Yeah, absolutely. One of my friends, Leonard Wanchikon, has this African School of Economics, kind of to sort of fill this gap of like advanced methods in Yukon and like in Africa. So he's having some success. I don't know. All right. Let me do this one topic, which is now we're kind of moving on to a different topic, which is kind of a classic topic. This is another paper by Rubinstein. This is attributed to him and this guy Stahl. This is Rubinstein Stahl bargaining model. This is sometimes people call it the alternating operability. Okay, so this is now we're moving away from the whole. I guess we should do some examples. Maybe we have time to go do some examples of income information games and stuff. But this is a different kind of topic. This is just a pure classic thing which everyone should know, which is bargaining. There's lots of times you're bargaining in life, et cetera. How do I model that? So I think, like if you did Barry's class, you did the Nash bargaining solution. So that one way to think about it is, those kinds of models are, say that like you make this graph, which is like I don't know. This is my utility and your utility. And say we're splitting $100 or something like that. So then what you do is you write this thing which is like, these are the set of bargains you would create. Remember this? So in this case, like this is where I get all the money and you get 0. This is where you get all the money. Okay? And this is maybe like 50-50 or something. Okay? So in this bargaining model, there's a set of things you can achieve, right? And plus you have something, do you remember this?
Yeah, what we did was we saw like a few graphs like that.
Right.
Where that's what we
Yeah,
did.
exactly right. And then, so one of the aspects is what you're bargaining over, and then there's another aspect. Do you remember that?
Is it signals?
No, there's nothing signaling. No, it's just so that here there's no incomplete information. Just straightforward. We have it to $100. You can think of it as a buyer and seller, but we need to both agree in order to split this thing. So the other thing, which is usually, I don't know if you remember, is usually, it's called a threat point. Have you heard of this thing?
Right.
Yeah.
Oh,
So the
the
threat
you
point is,
describe it, I recall it, I don't remember that term.
huh?
I don't remember that term.
Well, sometimes people call it something else. Sometimes, what's the word for it? It's like, BAFTA or something, BAP. It's like best alternative without agreement or something like that.
Yeah.
You heard of this?
Yeah, the best alternative, yeah, like outside an agreement.
Yeah,
this is the
exactly.
best alternative, yeah, I know that. That's the BAFTA.
Yeah, best,
Or BATNA, sorry.
BAFTA, exactly, best alternative.
BAFTA's like the British.
Exactly, BAFTA's like the Grammys. Best alternative if no agreement. Okay, so for example, if the best thing, so if we walk away from the deal, you know, we have to specify everything in there. So let's say that if we walk away the deal, I will get like, I don't know, 20, maybe I'll get 30 for labor. And then you'll get 20. Okay, so we're spending $100, but if there's no deal, I get 30 or 20, something like that. And so with the Nash bargaining solution, and actually this is the iconic bargaining problem. You have a set of things you can bargain over, but if there's no bargain, what will happen? Okay. So the Nash bargaining solution and other kinds of concepts basically say, given this set, given this point, what can I predict? And kind of, it makes, it says that we just make sure obey certain axioms. All right, so what we're doing in this is kind of another approach, which is to explicitly model kind of a process of bargaining. So this idea is, say that, let's just do, I don't know, like, say that we'll simply split, instead of $100, say just two people bargain over $1. Okay. If there is no agreement, we'll just get. So in this case, the threat point is 0, 0. Okay. Or the best alternative is there's no agreement. Okay, so under the alternating offer bargain model, what happens is one makes an offer, say. Okay, so one can say, 15 for me, 0.5 for me, 0.4 for you, etc., or 0.6 for me, 0.5 for you. Something like this. Next one. Okay, then two can either accept or reject. If there's a reject, then you get the third point. It's 0, 0. If two accepts, then you simply get the class. Okay, so
so we're starting at 1.
yeah. So I would think if there's many possible things coming out of it. So there's many possible things you could take, but 2 only has 2.
And the 2 will respond to each of those offers in the same way.
No, it doesn't have to be the same. 2 could say, I'm going to accept some offers, but not others. Yeah. So for example, so really 2 is needed to accept. That's what's going on here. Does this make sense?
Okay, so X, because X and 1 minus X is kind of the difference.
Yeah, exactly. So we're splitting $1. So for example, 1 could offer, for example, I don't know, 0.1 to himself and 0.9 to the other person. Could be 0.2. Okay, for example, so let's just try to solve this with backward induction. What will 2 do here?
Oh,
Yeah, because 0.9 is better than 0. That's a great deal. How about here? Also, right? In fact, 2 will accept any offer as long as what? 1 minus X is bigger than 0, right, exactly. 2 will accept anything as long as they're getting something out of it. So basically 2 accepts.
And in this game, number 1 is the offer.
Right. Exactly.
Kind of like receiver, and like we did last.
Oh yeah, well that's a different model together.
Yeah,
Exactly. Yeah. In sender and receiver, there's information going on. In this case, there's no input information. One just simply makes the, so we're specifying it. One makes an offer, 2 says accept or reject. So 2 accept anything which gives themselves 0 or 1. Okay. All right. So if 2 is playing this, what is 1 going to do? Of all these things, so Of all these things, one could, huh? Yeah, the maximum,
Yeah.
right? So 2 is going to say, I'm going to get it all and you get 0. Or maybe you get 0.001. So 2 will accept that. So given this, one offers 1.
I feel, sometimes I think this way, and I think it's wrong. Sometimes I think that can one of the players, can this be like a thing where, or is there some kind of concept where the other player is spiteful?
Oh yeah, sure, of course.
And like they won't allow, if I'm getting like, crumbs and I see take the entire loaf,
Yeah, sure.
it's still better than 0.
Right, sure, absolutely. So yeah, you 2 could play a strategy saying, I will accept no offer below the 0.5. And if that's the offer, what will 1 do? So 2 says, I will not accept anything, well, I say below 0.6, for example. If that's 2 strategy, what's 1's best response? What is 1 going to do?
I think one's best response is to get as close as possible to 0.5.
Okay, so 2 says, I will not accept any offer. They're spiteful. Anything which gives me lower than 0.6, I will not accept. I will refuse.
So it's 0.4.
Yeah, exactly right. So 1 will just have to kind of go along with that. So that's a Nash equilibrium. However, it is not a. So it's a Nash equilibrium, but that equilibrium. So there was 2 spiteful says, I'll not accept anything but lower than 0.6. 1 says, okay, well, I'll give you 0.6. Given what 1's doing, 2 is best responding, given 2 is responding. 2 is doing 1's best responding. It's a Nash equilibrium, but there's a criticism against it, which is what?
Based on what?
What do you think? If 2 says, I will accept no offer below 0.6, there's a criticism against that.
I think one could just say no.
Well, no, sure, 1, but 1 is best responding, but, so that is a Nash equilibrium. It's not, there's no rationality, so to speak, rationality. However, it is not, how do we solve this?
Backward
Yeah,
integration.
exactly, right? That's not something perfect, right? 2 is basically saying, I'm going to, if you give me 0.5, I'm going to refuse, but that's not credible in some sense, right?
Yeah.
And, so 2, in some subgames, 2 is not. Okay, so this is the only subgame perfect. Okay. All right. Okay, so this is pretty straightforward, right? It makes sense if you have the power to make an offer, and once you make the offer, then the 2 says, well, yes or no, then person 1 has a lot of the power, right? Has 1's driving the bargain. However, do you think this is a reasonable model of bargaining? Realistic. Well, so that 1 minute, I've seen that Netflix show, The Ultimatum. Just make an ultimatum and some stuff's up. Do you think this is realistic? No. Yeah, exactly. It's more of a back and forth. Right, exactly. So 1 can make an offer, 2 can accept or reject, and then say 2 accept is over. But if 2 rejects, then 2 can make an offer. So let's make that. So 1 either makes some sort of offer like this, a wide variety of things. Okay. And then give this 2 can either accept or reject. If 2 accepts, then that is implemented. However, if 2 rejects, then 2 can make an offer of 0. And let's see what that look like. Let's say, okay. It'll be like, say, I'll write it down like this: 1 minus y, y. So 2 says, okay, if I accepted your offer, then we'll just get x and 1 minus x. However, if I reject it, then I'll make an offer of my own. Okay, and then 1 can be accepted. Okay, if 1 rejects it, it's 0, 0. Okay, if 1 accepts it, then it is 1 minus y, y. However, there's one little wrinkle we're going to add, which is that we're going to say that this takes place in time. Okay, so if we get an agreement here, then it's no problem. But this is like the first day. So 1 makes an offer, 2 accepts or rejects. If 2 rejects, then we have to spend a little time. Then the offer comes the next day. And so the idea is the next day is, in present terms, a little less valuable. So in other words, I'd rather get $1 today than $1 tomorrow.
What is, so the way I think about this is, what if 2 wants to make an offer? So regardless of what 1 ever says,
Right.
2 will always say no because they want to make the
Oh
offer.
yeah, they could do that, for sure. Yeah.
And does that affect how the this game goes. And the other thing that I had in mind is, what if two was in a room and receives the offer and then isn't told what happens if he says yes or no?
Oh,
And then, but behind the door, they know that if he says no, they're going to give him the ability to make it. And maybe too complex, but I'm just trying to see under what conditions two's motivation is to reject, because
oh, I see.
it could be that his utility in by rejecting is higher than accepting.
Yeah, that's true. Okay. Oh, so let me see. So let's take your question. So then, okay. All right. So the first one was what? It was. What was it again? It was whether two. So yeah, two could reject an offer here and say, "I reject your offer, even though it's good, because I want to be in the driver's seat, so to speak." Is that what you're saying?
Yeah, exactly.
So this framework does allow that to happen. So if the offer is poor enough, two could say, "Well, that's not good enough. I'd rather just go back and give me the situation where I get to be."
Yeah, especially where, because the way I think about it is, because look at the final thing.
Right.
X or one can't respond to the deal.
Right.
One is stuck with getting
right.
either zero.
Yeah.
So in two's position, I can get myself like 99 and give you one.
Yeah, absolutely,
You know?
absolutely right, exactly. So two can easily think, well, I'm not going to, here I'm just sort of stuck, but I have to accept anything above zero. But here two can say, well, you've got to give me at least a pretty good deal, otherwise I'll just reject it, and now it's my turn to kind of, to be hard on you in some sense. Okay. So the one thing I'm going to add is that, so the other thing you said was something about like, what if two doesn't know whether they'll have the ability to make an offer and stuff? So that is not, here there's no uncertainty about anything. It's just, but you could build in if you want.
Really?
Yeah. Say there's some probability that.
Because I was thinking about the bubbles, like putting a bubble around A and R, or like something, not A and R, because obviously you know what's going to happen, but I mean a bubble around, you don't know what happens after you.
No, right, for sure. Yeah, maybe two doesn't know, like, maybe it's possible that two will, then the whole bargaining thing will stop or something. Maybe, so two's thinking, I'll accept or reject, but it's possible that I won't have the possibility of making an offer. You could model that, yeah. In fact, okay, so I will tell you, so there's a way of interpreting the next thing I'm going to say in those ways, which is, so the idea is that these numbers are slightly different, which is that every day this kind of goes on, the pie shrinks, so to speak. So there's this thing, have you heard the term discount factor or discount? Yeah.
No, but I can understand.
Yeah. So the idea is at this point, it's not 1 minus y, but rather like, I don't know, some number less than, say, this is 3/5. What does this mean? It means that if we make a deal tomorrow, it's
3/5 of.
Yes, it's worth 3/5 of what it would be today.
So two slices of the pie are gone.
Right, exactly. Exactly. So I just come up 3/5 out of thin air, but it means that, like, yeah, $1 tomorrow is worth 3/5 of it today. Okay. All right. Sort of makes sense. All right. So let's solve this game. At this point, what does one do? And so actually, there's a bunch of offers two can make. What is one doing here? So they're always choosing between 0 and this number, right?
Always accept.
Right. So they'll always accept, again, just like before, they'll accept anything which gives them more than 0. So one accepts anything which gives them 0 or more. Okay. So that's pretty straightforward. How about 2? What does 2 do?
Wait, you mean after rejecting?
No. This is, okay, so one is, okay, so if 2 gets the chance to make an offer, 2 has to think, well, I mean, 1 has to accept it.
Yeah.
But since 1, this is the end of the game, 1 will accept anything which gives themselves 0 or more. Right.
I think at least what we can do is 1 minus y, which is what 2 gets, or wait, y is what 2 gets, right?
Right. 1.
So you can model it as like y is greater than 1 minus x, but but at the same time smaller than what the full pie is.
Yeah, okay. I mean, so there's x's, we're not even dealing with x now. This is just the second period. If we get to this period, it's actually just like this, right? We got to the second period, 2 gets to make the offer. So it's a little simpler what you're thinking. 2 makes an offer. The only constraint on 2 is that 1 has to accept the offer. And 1, we just said 1 will accept any offer, which gives them 0 or more. So therefore, if you're 2 and you're thinking, oh, 1 will accept any offer which will get at least 0, what are you going to do? What are you going to offer?
Give them like, just about.
Yeah, give them 0. So 2 offers. 0 like this, right? Did I do that before? 0 for person 1. Okay, and then y, leave a 1. Right, so this is y is 1. Does that make sense? Okay, all right.
So 2 will kind of all, yeah, they will all offer that.
Yeah, yeah. If you're the last person to make the offer, you'll always just give the last person 0 and give your things up there. Okay. Now let's go back now. So this is all the last period, which is exactly the same as this one. Let's bring it back over here. Now this is period 1. This is like day 1, right, so to speak. Okay, if you're 2, what are you going to do except to reject here? Okay. Well, what? This is what you're talking about. If you accept, you'll get x and 1 minus x. If you reject, what will you get?
0, you'll get 1.
Well, you'll get 1, but tomorrow, right? So y will be 1, and in the end, you'll get this what? 3/5. Does that make sense? Okay, so you know that if you reject, you'll be able to have the power to make an offer, and therefore you'll get 3/5. Okay? You'll get 1 tomorrow, which is worth 3/15 today. So therefore, what will you do here? Will you accept something lower than 3/5? No, right? You will, as long as it's 3/5 or more. So now your thing is 3/5, right? If you get something higher than 3/5, you'll get it, right? So you will accept. Does that make sense? Because 2 knows that if they reject, they'll be able to make the offer and get the whole pie to themselves. That pie tomorrow is worth 3/5. Okay, so given that, what is 1 going to do? 1's thinking, okay, I have to make an offer to 2. If the offer is really low, 2 will reject it, and then 2 will have power and get it all for themselves. So I know that to make 2 accept the offer, I have to give them at least what?
If you're 1.
Huh?
If you're 1.
If you're person 1, you're making an offer?
Then you will basically have to give them, 3/5.
Yeah, exactly right. You're picking 3/5, exactly. So because anything lower, 2 won't get. Exactly. So 1 offers 3/5. So what happens is 1 offers 3/5, and then 2 accepts it. Okay. So and we end up happening. So it gets 3/5. Right? So okay. So this is interesting. Before 1 offers 1 0, but if you just had 1 stage of bargaining, 1 offered everything to themselves because 2 doesn't get it. Oh, I'm sorry, I take it back. 2 gets 3/5, the other person 2 3/5, I'm sorry. Okay, does this make sense? Okay. So one has to offer 2 at least 3/5, and that leaves person 1 with 2/5 of themselves. Okay. That makes sense? Let's do a little thought exercise. If this 3/5 was like 9/10, how would it change? Instead of 3/5, it's 9/10.
It would be then 1 would take 1/10.
You're right. It would be like this. Right? Now, what does 9/10 refer to? Okay, so 3/5 means the future is kind of decaying at a rate of 3/5. 9/10 means it's decaying more slowly. Does that make sense? So it means that you're more patient. Right? So like, if you're super impatient, it means that you're like $1 million tomorrow, you'd rather have $1 today. That's super impatient, right? But if you're very patient, $1 million, tomorrow is just a little bit less than. Yeah, exactly. So 9/10 corresponds to more patience. So if people are more patient in general, that is, sort of this pie is decaying much more slowly. Who benefits from this? Would 2 prefer this or this? The bottom one, right? Exactly. If you're really patient, then you kind of have greater interest in making it go all the way to the end. Because going and making it go all the way to the end doesn't cost you that much, because you're very patient. And at that point, you have full power. So that's the point at which you use it, so to speak. Okay? All right. Let's see. Let's do another one now. So how about now, one offers, then two accepts or rejects. Then one offers, I could make it cheap, but we'll just make it, say, two accepts. Why not? So then we, instead of two rounds of bargaining, then we'll have 3 rounds. Okay, so we can make it a tree. Let's see now, we'll just write it down as kind of a table. So now there's 3, so in this one, the first one just made an offer, then it's over. 2 accepts or rejects, that's it. In this one we have 2 rounds, 1 makes an offer, 2 accepts or rejects it, 2 rejects, 2 makes an offer. Now we have 3. Okay. All right, what happens? Well, we'll just backward induct like we did before. In the last round of bargaining, what will it 2 accept if it's the end?
There's a third round.
Yeah, so there's 3 rounds, but we're talking about the 3rd round. We're just going backward induct.
And it's decaying at the same rate.
Say it's 3/5, yeah, exactly, right. So kind of decay. So discount rate is 3.
So in this scenario, I think 2 can win. 2 can offer,
Uh-huh.
take 2/5 and offer 1/5
Uh-huh.
to 1, right? Because 1/5 is going to offer 1/5.
Well, okay, let's see.
I'm just thinking, so if it goes down 2/5, then
Uh-huh.
it's going to be 1/5 left over, and 1 is going to kind of want,
Uh-huh.
1 is going to want 1/5, or the large portion of it. 1/5 times 6,
Uh-huh.
times x, sorry, and then 1/5 times 1 minus x.
Yeah. I see what you're saying. But we can, so there's math behind this kind of, but let's just take it from the back and see, okay? In the last round, what is the offer made? Well, first of all, what is 2 accept or not? So 2 is, if 2 accept or rejects, if 2 rejects, it's over, right? So 2, what will 2 accept in this very last round? Yeah, anything 0 or 1, exactly right. So in this case, 2 accepts 0 or more. Therefore, what will 1 offer in this last round?
1/0.
Exactly, 1/0. All right, now, so that's what's going to happen. This is always going to be the case. In the last round, the person who gets to make the offer basically says, it's all mine, and then, you have no choice. Okay, the round before that, now, what will 1 accept?
And we're taking into account the discount.
Yeah, exactly, right.
So is that within 3/5 or more?
Yeah, exactly. You have to give, 1 will accept 3/5 or more. Right? So therefore, what will 2 offer?
2/5.
Yeah, 3/5 for themselves.
Oh, yeah.
Yeah, 2/5 of themselves, exactly. Right? I think this is kind of like what we did over here, right?
Yeah.
It's kind of cool. Now this is the interesting thing. Okay, so now, this is what happens in the second round. What happens in the first round? Okay, what will 2 accept? If 2 refuses, what? 2 will get, what? 2/5. Right? Tomorrow.
So we're again using the discount?
Yeah, exactly right.
So like 3/5 of that?
Yeah, exactly right, exactly. So, okay, think of it this way. This is the first round. 2 says, you can't lowball me too much because I'll reject it and then I get to have to make the proposal power. But even at that point, I can't, it's not like this. At that point, I can't lowball you too much because then then you can refuse and then you have the power. So it's this kind of thing, right? So 2 can reject anything. If 2 rejects, 2 knows that 2 can get 2/5 of themselves tomorrow. Okay? So therefore, you've got it, 2 will accept anything which is above 3/5 times 2/5. Okay? So it accepts I think it's what, 6/25 or more. Does it make sense? So then what will one offer?
19.
Yeah, 19/25. So. Does that make sense? Now let's do it a comparison. Okay, so this one,
I just have kind of a question, and I don't know if you can put, if this can be fitted in, but
sure.
I guess the rational way of looking at this is that 2 will always accept anything over 0.
At the end, yeah.
Yeah, and will accept anything at the very end.
Right.
But can we say that, could it be that 2, because even, I guess 2 has some power there, right? 2 can say no and no one gets anything.
Correct.
Can that, is there a way of explaining that? Because I feel like the rational, the model says that 2 will always pick not 0, but are there conditions where 2 can pick 0, 0? Or that's...
No, I mean, it's kind of what you're saying is right. It's like, okay, say that you're literally the last person, okay, and you know that if you reject it 0, 0, you can still play the strategy, I want at least 0.5.
Yeah.
And then if you play that strategy, it'll affect all this stuff.
Yeah,
right?
exactly. And like I guess one has to be able to
Uh-huh.
perceive what 2 wants.
Yeah, right. So, okay, so in that situation, that would be a Nash equilibrium, and in a Nash equilibrium, we're assuming that everyone knows everything else. Like, you know my strategy, I know your strategy, no problem. Okay, so in a situation where it's not clear if I know what you're doing, then we're playing a game, but a Nash equilibrium will not necessarily apply to that situation. Okay, but what we're doing here is we're relying heavily on subgame perfection, which in that subgame perfection, there's no issue. That's the whole point of it in some senses. You're assuming away people doing stuff like that, for better or worse. I mean, so people can sometimes say, well, I know this is going to hurt you and me, but I'm just going to insist on this. So that's not happening here. And there's even theories about that, like some people say that's why people, one of the reasons we have emotions is so we can credibly say, if you piss me off, I'm just going to do something which is bad for both of us. Something like that, and that's how, emotions allow us to do that kind of stuff, make threats which don't seem rational or credible at the time. Okay, anyway, if we rely heavily on subgame perfection, this is what we have. So what the result is what, 19/25, 16/25. Okay, so how do I understand this? In this case, one gets to make the last offer. So if you get to make the last offer, you'll always be able to be in a relatively good situation. Because in the end, you get to have all the power. However, if there was just one offer made, right? Okay, like in this single case, like if there's just one offer, okay, here, being able to make the last offer, it gives you like everything, right? Whereas here, being able to make the last offer gives you an advantage for sure, but it's not as big as before. Does that make sense? Okay, so every time, in other words, every time you allow another round, kind of the power imbalance gets a little more even. Okay, because the impact of having the power at the end is lessened. Okay, let's do one with, should we do let's do one with 4. Okay, so getting discount rate is 1. So let's say that now 1 offers, so there's 2 offers. If there's rejection, 1 offers, and 2 offers. Okay, then, so let's do the same thing. So again, discount rate is 3/5. Okay. So this is another 4 rounds. I get to make an offer, you reject it, then you get to make an offer, if you reject it, I reject it, then etc. So it's like literally 4 rounds of bargaining. In the last round, what's going to happen?
One will accept at least 0.
Yeah, exactly. And so therefore 2 offers 1.
0.
Exactly. That's always me. Okay, so what is in the third offer? What will 2 accept?
At least.
Exactly, 3/5 or more. So therefore 1 offers what?
2 is.
2/5, 3/5. Okay. In the second offer, 1 knows if they refuse, they'll get at least 2/5, right? Okay, so therefore you got to offer what? So one will reject anything which gives them, which is worse than the 2/5 tomorrow, right? Which corresponds to how much today?
6.
Yeah, 6. Okay, so 2 has to then, since 1 will accept anything with 6/25 or more, 1 will have to, 2 has to offer 6/25 to 1. And then 2 gets how much?
19.
Yeah, 19/25. This is just what we did here.
Mhm.
Now, finally, the first round, 1 missed to make an offer. 1 knows that if the offer is rejected, 2 can get this, right? So therefore, what is 1? So 2 will accept what? Whatever this thing is times 3/5.
Yeah.
I think it's 57 over
Yes.
125. What? I think it's right. 3 times 19 is 57. Okay. So therefore, what does 1 offer? Whatever this number is. Is that right?
60.
Yeah. Okay. Does this make sense? Okay, so what's interesting, look, compare this with this. This is a situation, so there's 2 rounds of bargaining, here there's 4 rounds of bargaining. In both these cases, 2 gets to make the last offer. So you expect a 2 to kind of milk this power, right? Okay. In this situation, 2 gets what? Okay. 2 gets to have full power in round 2, and that makes person 1 offer them 3/5, right? Which I think is 0.6. Okay, so 0.4. How about here? What do we end up with? Okay, do you want to calculate this? Anybody can? What is it? 57 over 127.
Wait, 127 or 125?
Oh, right, 125. I'm sorry. Thank you. Thank you. This is 0.456, and I guess this is going to be 0.534. Okay, what's interesting? Look, so let's see, hold on. What? 2's power goes down, right? Okay. So 2 has still, I guess, I don't know. Yeah, it's not too bad. So 2 gets to have the last offer. Okay, but because there's these sort of network of, like this series of offers, 2 doesn't get to milk it as much as over here. Right? Makes sense? Okay, I'm thinking, is this should never be 1.5? No, I think it's okay. Okay. I think it is okay. All right, does it make sense what we're doing? Okay, so the next step is now, so I think it makes sense, yeah? So one division is as this series of back and forth becomes longer, then you get less, you can't milk that power of the end as much, right? So you get, obviously you have a lot of power if you're at the end and you make the last offer, right? In both here and here, for example. But in this case, the fact that there's 4 offers, 4 rounds of bargaining, dilutes person 2's power. Okay? Person 2 would still rather have this, I think, than this, right? I think, what's 6 over 25? That's like...
It feels like 2 would maybe, not 2, but I think that everyone would prefer the first offer. Because over time, it's been the offer.
Yeah, you're right. So actually, what actually happens, 1 makes the offer, then 2's accepted. So we're not going down this road. Okay, but this is kind of what you would, this is off the equilibrium path, so to speak, right? The reason that 1 is offering 68 over 125 is because if they offered anything lower, then 2 would be, and 2 is doing this because of, okay. Does that make sense? Okay, all right. So the next step is what? Do you want to do it with 5?
Fifth
No.
round.
We could keep on doing it, but then you can kind of see the point is. So then,
It all follows like the same.
yeah, exactly. So you could do 5, 6, 7, and that's fine. And I think that's kind of what Stahl did. He said if you do this, but then there's an obvious question: is like, when do I stop, right? And so then you can ask the question, what if you could bargain forever? Okay, like so, all right, so let's say there's as many rounds of bargaining as possible. Okay, so let me see if I can do this. Okay, so the idea is this. If there's, there's unbounded numbers of bargaining. So what happens is that one makes offer, then two accepts, and then two offers, one accepts, and then one offers, two accepts. Okay, so this is the idea. How are we going to solve it? The idea is the following. Okay. The idea is that if one offers to accept, then we have more and more of these things like this. So the idea is this kind of like an induction kind of thing, which is like, this is a long, long game, but if they reach this part, it's as if we were the same as this, right? So in other words, this is stage 1, stage 2 of bargaining, stage 3 of bargaining. Stage 3 of bargaining is exactly the same as stage 1 of bargaining. Right? It looks exactly the same. Okay, in this case, stage 4 bargaining is different from stage 2 bargaining, because stage 4 bargaining might be the end, right? But in this case, it's not the end, right? So if you can bargain infinitely into the future, bargaining process at stage 4 is exactly the same as stage 2. Does that make sense? Because it looks exactly the same. It's like, oh, I get to make the offer and then put the people. Okay, so then we're trying to use this trying to solve what's going on. Okay, so let's see. What we're going to say is we're just going to use some numbers. Okay, so say 2 accepts V2 or more. And then, let's see. Oh, I guess, well, maybe I'll do this way. Okay. Say this is worth, I'll do this way. V1, V2. Okay, so I guess 2 will accept V2 or more, and 1 will have to offer them 1 minus V2. Anyway, the idea is, so what we're going to say is, if we reach this game, this is what the payout switch will be reached. Okay? Right, at that point. Is that okay? I'm just going to say, just assume this. So for example, I guess over there would be what, for example, 2/5, 3/5. Okay, now let me see. If you reach this point, and 2 gets V2, and 1 gets V1, what will 1 play at this point? So what will 1 accept?
Delta V1.
Yeah, exactly, delta. Oh, if we're keeping the 3/5 thing. So this is the, have you seen this delta? That's the discount factor. So this is 3/5. Keep it that way. Okay. So we're just going to assume straight up that from here, this is worth V1 and V2 to people who've reached that. So in this place, 1 will accept anything which gives them 3/5 of V1 or more, right? Because they know that if they reject, they get V1. That's what. Okay, so therefore, what does 2 offer here?
Three fifths V1 and 1 minus.
Yeah, 3/5. Exactly. Do you see what we want to do? Okay. So we're just going to assume this is what it's worth at this point. If we reach this point, 1 will get V1. So therefore, 1 accepts 3/5 V1 or more. Therefore, 2 has to give at least person 1/3 V1. Yeah? And this is how much 2 gets by themselves. Okay. Bring it up to here. What will 2 accept?
3/5.
Yeah, exactly.
1 minus.
3/5 of 1 minus 3/5 V1. Okay. That 1 will have to offer what?
1 minus that whole thing.
Yeah, exactly.
So
1 minus 3/5. This whole thing.
Would this be mapped on a graph to look, would this all be mapped on a graph, or how would it, to visually see the development of how?
What do you-
If I wanted to see the kind of the value of V1
Uh-huh.
develop or decrease.
Oh, no, so,
The
okay.
rate, like the actual mathematical rate, to see it on that
Okay.
graph, would that be graphed or?
So the idea is that this V1 is, okay, V1 is not changing. So the idea is that, okay, so, okay, let's go back over here.
Yeah, sorry, I
No,
think
no.
I said it wrong.
Uh-huh.
V1 isn't changing, but
Right,
the value, the value itself is changing. V1 is a portion,
right,
represents like a portion of that.
right.
I didn't want to.
Oh, no,
I
okay,
didn't want to make you think that I
no,
didn't.
no problem. Okay, let me see. So, okay, so what's going on here? The key idea, okay, so here we understand this, I think, right? So what's different here is that at the end, so for example, 2 offers this at the end, that's different from offering this at this point, right? Because this is really the end, whereas this is 2 from the end. These are all slightly different. Yeah? As you get toward the end, for example, having the offer gives you more power, right? If, for example, if you're at the very end, you have full power. The idea is if we have an infinite number of possible voting or bargaining rounds, there is no end. So being able to make the offer at time 3 and time 1 is literally exactly the same. It looks the game, so the game at time 3, you do all this stuff, is the same as the game at time 1. Does that make sense? The only difference is that it's 2 things in the future. Yeah. But in terms of the strategic aspects of it, it doesn't look any different. Does that make sense? Because I think, you're not closer, in other words, when I'm time 3 or time 5, time 7, it's not like I'm closer to the end or something like that, because there's always going to be more stuff. Okay, so that's the idea. So therefore, we could keep on doing this, but we can just say, okay, let's just stop it at this point, this is round 3, and simply say that at this point, this is what will happen, okay, in terms of people's utility. One will get V1, 2 will get V2. And the idea is we're going to kind of solve for this in a recursive way. Okay, all right. If this is true, 2, and so 1 will get V1 if it gets to round 3. Therefore, at round 2, 1 accepts 3/5 V1. And therefore, the 2 makes this offer. All right. So this is a round 2. Therefore, if in round 1, person 1 has 2 will accept this, 1 minus 3/5 V1 times 3/5. And therefore, gives I guess what's easier to do person 2 first, right? 3/5. 1 3/5. V1. This person 2. And 1 offers themselves 1 minus 3. Does that make sense? Okay, I think that's right. Let's see if that makes sense. Okay, yeah, that's good. All right. Now, how do I solve for V1 and V2? Remember, the idea is that this is kind of the same as this, right? The game at time 3 is the same as the game at time 1, time 7, or whatever, time 5. So how can I solve for V1?
So because it's infinite, the solution will be different.
Huh?
Because it's infinite, then the solution.
Well, go ahead, no. Okay, the idea is that, okay, if we reach this point, person 1 will get V1, 2 will get V2, right? Okay. But that should look the same as this. Okay, so we said, if at time 3, okay, this is what the past people will get, then in time 1, these are the past people will get. However, this and this should be exactly the same. Make sense? So how could I solve for V1?
So those 2 are the same if you include the discount factor, or just,
Well, actually, I don't think we need to include the because this,
or
right?
is it already?
Yeah, exactly, right, so yeah, so the offer here is like what, this is what one offers here, yes? Okay. If the idea is that this is the same as this, what can I say?
Then you just set V1 equal to that.
Yeah, exactly.
Yeah.
Yeah, exactly. We just say this number is equal to this. It's as simple as that. Okay. Does that make sense? It's like a recursive thing. Yeah. Okay. So given that person one makes this offer and this is where V1, V2, person two has to offer this. Given that person one has to offer this, but this should look the same as this. So therefore, this number should be the same as V1. Okay, so let's do that. So V1 equals 1 minus 3/5. 1 minus 3/5. Okay, right, that's right. What is V2 equal to? V2 should be equal to that. Okay.
Let's solve for V1.
Yeah, let's just solve for V1. What do you want to do? I just expand. This is just now pure math. 1 minus 3/5, right? Plus 9/25. I think it's right, man. This becomes 16/25 B1 2/5. So B1 is equal to 2/5 times 25/16. Hope this number is less than 1. I think this is what? 5/8? Huh?
Yeah.
Yeah, 5/8, yeah. What's V2? Well, we just put in here. V2 equals 3/5. 1 minus 3/5 times 5/8. 1 minus 3/8 is 5/8 is 3/8. I guess it's not surprising. Yeah. So what offers? The offer will be it's going to be what? 5/8 3/8. All right, does that make sense? Let's see now. Can I compare this with this over here? Okay, this is what? 0.534, 0.456. 5/8 is what? So I think, yeah, exactly. This is 0.3. Okay, does this make sense, kind of? Does it make sense that, so in this case, if you have infinite numbers of bargaining, then one does what? This is what? 0.76, right? Okay. All right. If you have infinite numbers of bargaining, infinite stages of bargaining, then one does better if there's only 3, right? Well, one does best obviously because there's just only 1, and they get 1, right? If they get 3, they get 0.76. Okay. So it makes sense because in this 3-round thing, one has the last offer, makes the last offer. Okay, how about person 2? Person 2 here got 0.6. There's 2 rounds. If there were 4 rounds, they got 0.456. In this claims they get 0.375. Okay, so remember, 2, you do get an advantage if you're the last person to make the offer. Okay, but that advantage decreases with the number of bargaining rounds. So in this case, if there's only 2 bargaining rounds, it's 0.6. So there's 4, it's 0.456. Something like that. Yeah. If there's many ones, it's 0.37. Does that make sense? Right, so I think it's working out. And the key thing here is that if there's infinite numbers of bargaining rounds, it's sort of this recursive relationship. That's what we're exploiting in some sense. Although we could just calculate it out like for do 80 or something, but then you can realize there's this number.
So basically what the model tells us is that the person who begins the negotiation always benefits.
Yeah, so here one does have, so in here there's no ender, right? No one ever gets that last little bit of power. Okay, but In this case, yeah, one does get a slightly,
So can we say that both 2 and 1 prefer to be the offer? Like,
yeah, for sure, if you believe this one. Okay, does this make sense? Okay, so now let's take another step in this. Now instead of the delta equals 3/5, what about delta just being as delta?
Oh, okay, so now we would insert delta instead of factor.
Yeah, exactly right. So what would change? Okay, so this is the same. This 3/5 is now a delta, right? This is going to be delta V1. This is going to be delta times delta. Okay, so now, oh, this is also. Okay, all right, I think it's fine. What changes? Now we just, this is just like, it's not the details. Instead of 3, this is how the delta. Okay. So let's solve the same way. The 1 minus the square is V1. Okay, so then V1 minus delta squared is 1 minus delta. So V1 is just 1 minus delta is 1 minus delta squared. Okay, and I can simplify this a little more too, because this is 1 minus delta over 1 minus delta times 1 plus delta. Right? I can factor that. Right? This becomes 1 over 1 delta. What's V2? V2 is equal to, oh, what is it? This thing, right? Delta 1 minus delta V1. This is delta 1 minus V1 is this, right? Delta over 1 plus delta. This is what? Put everything over the same denominator. Is it clear? I just got this. I'm just substituting it. I think this number is going to be just, this is just 1, so it's delta over. So for a general delta, it's going to be 1 over 1 plus delta. Delta over 1 plus delta. Okay, and those numbers up. And I think when delta is 3/5, it corresponds to this. Does that make sense? No, that's kind of fine. Now, let's think, as delta approaches 1, what does this number come close to? Delta, as delta gets close to 1, that means both people are very, very patient. Right? So it means that $1 tomorrow is worth almost $1.
Just before we continue, so a discount factor, so when you say a discount factor is 1 over 5, does that mean it decreases 1 over 5 or it decreases 4 over 5?
Oh, okay. Yeah, so that's a good point. If the delta is like 3/5, that means that if $1 tomorrow is worth 3/5 you today's. Is that right? Yeah, exactly.
Okay.
That's what it means.
So it's not the rate of decline.
Right, exactly. Sometimes there's a difference. This is the discount factor, but there's also a discount rate. Yeah,
So the factor, the rate would be how?
like a percentage. Yeah, exactly. So let me think. Is it? No. What's it? So $1 tomorrow is worth delta today. So if I did it in terms of a rate, what does that mean? If I take the 10% rate, a discount, that means that, yeah, $1 today is worth $1 tomorrow is worth 0.9 today? That means it did 10%? No, it means it, okay. Yeah, I think that's what it means, right? If it's a 10% discount, it means $1. Oh, what is a 10%? Well, you can think of it as an interest rate. An interest rate means this, $1 today is worth 1 plus R tomorrow. Right? If you think of, say, interest rates are 10%. Okay. So interest rates are 10% corresponds to this. This means what? So this corresponds to, so 1 over 1 plus R today means 1. So yeah, so exactly. If the interest rates are 100%, that means half a dollar today is worth $1 tomorrow. Right? So, yeah, so this, therefore delta is 7 is 1 minus R, with R as the interest rate.
So basically, the discount rate does not change, it just multiplies itself with the value.
Right, exactly right. So if my delta is 0.9, it means that $1 tomorrow is worth 0.9. $1 2 days from now is worth 0.81. Okay, yeah. So if interest rates are close to 0, that means like I can put $1 in the bank and I get $1.001 tomorrow. Like really low interest rates. R is close to 0, that means delta is close to 1. Okay? It means that little delta thing decreases, but it's very small. Delta is close to 1, what does it become close to?
1.
Yeah, half, right? Which sort of makes sense. The idea is if people are very patient and do this bargaining back and forth, the asymmetry of having one person being the first proposer is less, right? So that it becomes closer, just sort of half-half, split the difference.
What about delta's close to 0?
Yeah, exactly. If delta's close to 0, what does this become?
Just 1.
Yeah, this becomes like 1, 0, right? That means if you're very impatient, it means having the first mover, first offer, gives you a lot. Makes sense? Yeah, that sort of makes sense, right? Yeah, it sort of does. So that's a nice thing about this one. Okay, so in some sense, already we've gotten a lot. And if you had written, so it's a very natural model, but I mean, Rubinstein and Stahl were the first people to do it. And it sort of makes a lot of sense. It just really, you and I could have figured this out, had it been set up in this way, right? And you could have had this great paper too. Okay, so now let's see, can we do another wrinkle? What if, say person 1, they have different discount rates. So we have delta 1, delta 2. Okay, so for example, one might be more patient or impatient than person 2. All right, let's do the same thing. Okay, so in round 3, 1 offers V2. So this is the thing here. So if you're person 1, you know that if you reject the offer in round 2, you get to here. So therefore, what will you accept in round 2? Before it was like delta V1, right? But now it's delta 1 V1, exactly. It's your discount factor. Okay? It's all done. It's saying there's different discount.
So this is if each person is a
Yeah, exactly right. So I could be more patient or more impatient than you. Okay, so you have to give person 1 D1 V1. Then person 2 will get 1 minus that, I think. If in round 1, 2 rejects, 2 knows that 2 will get this next time. So therefore you have to give 2
Delta 2.
Yeah, exactly, delta 2 times this.
Oh, yeah.
Huh?
Yeah.
Yeah. Okay. And now person 1's is going to be what? So this is going to be delta 2 minus delta 1. Okay. Now person 1 will get what? I think just 1 minus that stuff. Yeah? 1 minus delta 2. There we go. Now, how do I solve for V1 and V2? The same thing, right?
Yeah.
It actually hasn't changed that much. So I have this equals V1. V1 equals 2. 1 minus delta 2. Okay. Right, this is just a one, variable. So V1 equals 1 minus delta 2 plus delta 1 delta 2. I think I have V1 1 minus delta 1 delta 2. This is minus delta 2. So V1 equals 1 minus delta 2 over just a minus 2. Okay? I think that's right. What is V2? V2 is just, I think, what, this thing, right? Delta 2 is 1 minus delta 1 V1. Equals 2, 1 minus, I'll put this all in one denominator, right? This is going to be delta 1 minus delta 1 squared plus delta 1 delta 2. So no, I take it back. What am I doing? Oh no, this is just multiplying. I'm sorry, I have to do common denominator. I'm sorry. So 1 minus delta 1 delta 2. This simply will just help here. This is simply delta 1 minus delta 1. All right. That's right.
So why were you again able to make that, like, you're saying that the two rounds are equivalent,
Right.
but not in the.
Oh, yeah,
final?
okay. Why couldn't I do that over here?
Yeah.
Okay. The reason is simply that the reason is simply, in some sense, you think this is easier, and it is easier because you can go to the end and work your way backwards. But in some sense, it's a little harder because if there's only 4 rounds, round 4 and round 3 are different, obviously, because round 3, 1 gets to make the offer, round 4, 2 gets to make the offer. But even round 4 and round 2, both of those cases, 2 gets to make the offer, but they're different because round 4 is kind of like, this is the end, so 2 gets to press the advantage as much as possible, right? Whereas 2, they think, oh, well, I can compress a little bit, but if I get pressed too much, then 1, rather than 1, you know. So it is slightly different. In each case, you know, these numbers are different, right? But the idea is, if there's actually, so this infinite thing it seems more complicated, but it actually is easier in a way because there's no reason why an offer around 24 should be different from around 22. Because if you look at the game at that point, it's literally exactly the same, right? It's not, see what I'm saying? So, because, you know, it's not like 24 has, if you run around 24, there's fewer rounds than around 22. That's
Yeah.
right. It's sort of, it's self kind of referential in a way. So, okay. It's kind of like saying, oh, like, well, you know, say you have these numbers. You know, the cardinality of numbers after 8 is the same as the cardinality after 6. Right? I think we're getting close. So we solved this. Now we're just following delta 2. Sorry, we're solving for V2. I'm doing this, I think this is equal to delta 2. 1, I'm going to put the 1 up there now. This is going to be, so this is going to be 1 minus delta 2. Now this minus goes inside, minus delta 1 plus delta 2. That's right. This is going to be equal to delta 2. These things cancel, it'll be 1 to 1. Okay, I think that's right. I think that's right. Yeah. Okay. Do these things add up to 1? I think they do, right? If you take this and add to that, that would be a delta 2 next time. Yes. Okay. All right. Well, now let's all write our objective. This is with the full kind of. Yeah. Okay. If delta 1 and delta 2 are equal, do I get this? Oh, they should. So if they're equal, like this is 1 minus delta over 1 minus delta squared, which is the same thing as 1 over 1 plus delta. Right? This would be delta minus delta squared over 1 minus delta squared. That will be same as delta over 1 plus delta. Yeah, so I think it works. Okay. Now let's think about this. Again, if delta 1 and delta 2 are close to 1, okay, this becomes, well, I guess both denominator and numerator become close to 1. Becomes like this. Yeah, it becomes close to half. So, do you want to do some? Yeah, I think that's right. Should I do that? If delta 1 and delta 2 are both 0.9999, it's this. Right?
It's the same.
So one thing we haven't done is what? If delta 1 is large, is taller, but delta 2 is small.
Yeah, if they're variable.
Right, exactly.
It's like a lot of pressure to keep it.
Exactly. So say that like delta 1 is like close to 0, delta 2 is close to 1. And then what's going to happen here? This thing becomes close to 1. Okay, delta 1 is close to 0, delta 2 is close to 1. Then, okay, what? This denominators are both close to 1. Say roughly. Okay, what happens here? Delta 2 is close to 1, delta 1 is close to 0. This numerator becomes 1.
Oh, it stays, it's 1 minus.
Yeah, delta 2 is close to 1. This number is what? Close to 1 also. So this number is, numerator is large, like near 1. Right? What about this number here?
0.
Yeah, exactly, right. This number is close to 0, this number is close to 1. I guess we're not really sure what's going on in the denominator, but basically it's the same for both, right? So this thing becomes close to 0, 1.
Wait, so D2, so delta 2 is a rate that is slow, right?
Right.
Oh, so because one has a lot of pressure on them, then they're going to accept anything.
Right, exactly right. So here, person 1 is very impatient. Okay? Person 2 is very patient. In that situation, person 2 gets everything because person 1 really is desperate in some sense. Right? Okay. What if delta 1 is close to 1? Delta 2 is close to 0. Then the solution becomes what?
Oh, just.
You switch around, this becomes 1. Makes sense? All right, so pretty good model, you know, from starting from simple base principles and doing this kind of recursive thing. Okay, if delta is the same for both, then you just simply show that if, as people get more and more patient, the result of the bargaining gets closer and closer to half. So which makes sense. It's going to become more of a symmetric situation. Person 1 will always still have do a little better than person 2 if the delta is that. Because they'll get a little bit of advantage for being the first person. What if people's discount rates are different? Well, in the limit, if you're really, I think we haven't done the full comparative statics, but in the limit, if you're really patient and your friend is really impatient, then you get everything. If I'm really patient and you're really impatient, then so bargaining very much favors the patience. I guess we could put this in a thing and just see like as delta 1 and delta 2 change, how these numbers change. Yeah, but in the limit you can see that for sure. Okay. Makes sense? Okay. Okay. So the end, essentially. This is Rubinstein's model, and well, still on Rubinstein's model, and when was this paper published? I think in 1989 or something like that. So another great paper by Rubinstein, and then, but I think it really gets at something which is pretty true, which is that in a bargaining situation, if you're impatient, then that's going to hurt you, right? Because obvious reasons, right? Because you lose more by going to the next round, so you can't insist on this, but not much on this round, right? And that kind of snowballs in some sense, right? If somebody knows you're going to be in a terrible bargaining position in round 10, they're going to try to get it to round 10. Yeah, and that affects what you'll accept in round 9, which will affect et cetera, et cetera, et cetera. Right? That's kind of the idea. So, yeah, so it's good to be patient. It's like, when you buy a car, they always say you go at the end of the month. Have you heard about this whole story? That because at the end of the month they're trying to get their sales figures up. So a car around January 31st is worth more than a car for them it is January 20th. And apparently this is actually true, because they really want to make their,
Actually, good.
yeah, exactly. Because around January 20th, I think, oh, maybe more people will come in and say, January 31st, it's like this person's not coming back. So I actually have done that, and you go there and you can bargain more because they have a low delta. For them, there's a big difference between January 31st and February 1st. February 1st is on a different pay thing, right? So they want their bonuses January 1st, so it's a big difference. They're totally willing, they don't want to go to the day, whereas you don't care, right? So therefore you're more likely to come to the situation. So that's sort of true. Let me see if I can show you the paper. Let's see. Good. Here, okay. So like many of these things I kind of show you before this is 1982. Okay, 20 years out, 40 years ago, wow, impressive. Okay, so bargaining problem. Okay. So all this stuff. It seems kind of let's do this. We'll do continuous. There's a lot of mathematical stuff going on here, I guess. You look at it. So when I read this paper, I'm thinking, oh, what's going on here? So this is kind of like, these are sort of axioms. This is like my offer, now your offer. Yeah, that's right. Oh no, these are times, so something like, yeah. This means that if t is the same, then I like more money versus less money. I guess that's what that means. Yeah. I think, well, this means if I have positive payoff, that means I would rather, this is future, this is now. It means I prefer that money now versus the future. That's what that means. T is fine. And all those things are better than zero now. Getting zero, very far away. Does that make sense? So all these things kind of make sense. But when I read this, I really always kind of find the example first. Okay, and I'm thinking, I'm not reading this. In fact, no one really reads this stuff because it ends up being much simpler than you think. Okay.
I think that sentence is just written, to make sure that the author is explaining it the best
Yeah,
way
right.
for himself.
Yeah, exactly.
I feel like the peer reviewers need to know that the author knows what they're saying.
Right. And there's an element of generality too. They want to make it as general as possible sometimes.
I'm curious. I'm sure you review a lot of papers that are like this. How would you, is there a thing that you would skip over because you know that whoever's doing this knows what they're writing in this section, and then focus on kind of, like where is the focus? Because I'm sure you won't focus on how they're describing the model, but you're going to do the math more.
Well, I would focus, the main thing I look for when I referee is there something which, like an example essentially. Whenever I read a paper, I'll look for the example first. Because that will kind of get an idea of something. I'm not too concerned about generality. I'm mainly concerned about, is there something here which has an underlying logic which I think is okay? And you'd be surprised that a lot of them don't. And so, like if there's no example, you just have to read the whole thing in generality and think, oh, what would be the example which makes this work? So I'm a very example-driven person, and actually most people are. But then, if you understand the example, you think, oh, then is this some special thing, or could this be, like, how generalizable is this? Like, does it make sense to them? They're doing a general argument, and then I'll go through. But certain things I will never read, which is, if they try to prove something, I will not go through the proofs or something, because it's a lot of work to do that, and it might take weeks, and you just sort of trust. But as a result, sometimes people make mistakes in proofs, or just you don't even know how to prove things, and no one will ever catch them. So it's kind of not a good thing.
Where was this? What's this journal?
Oh, it's a well-known. This is one of the prestigious journals in economics, Econometrica.
Where is the journal?
Yeah. So it's kind of like yeah. So like anybody would be proud to have a journal article in Econometrica. I don't have one actually. I have some similar ones, but not in this journal. Okay. Anyway, so let's see. Reading. Okay, I'm thinking, where is there something which looks good? And then finally, I look at this. This is something I can understand. Literally this one thing. And that's, I think, what,
Might be right.
that's this. So it's only coming at the, this is sort of a special case when people have fixed discounting factors, right? And so, yeah, so the rest of the paper is about a different kind of discounting or, more general discounting. But if people have fixed
Also,
discounting.
he like also talks about each individual has a variable discount.
Right, exactly, right, yeah. So you could have lots of different ways of thinking about preferences over time. And that's, so he's arguing, yeah, he shows that you can still do this model if people are not like that. But if people have this particular one, which is, I think, is fine and definitely illustrates the idea, then this is the core of the thing. So you can understand the core of the argument in a relatively limited context. And you don't just understand the core of the argument in a very broad context, just the simple way. And then you think, oh, but I can understand it. I could actually do this myself. And so, yeah. So that's it. So yeah, so I literally, yeah, oh, yeah. This is what we saw. This is like V1, like 1 minus, I think it's something like that. Yeah. So, this is to me the heart of the paper. If you understand that, you understand like 80% of the paper, and then you realize everything else is just kind of like an elaboration on that. But that's the core. The core of the idea is that, again, in round 3, it's the same as round 1, but just two there's nothing different strategically in round 3 versus round 1, right? Or round 5, round 7, they're all the same strategically, right? So, in other words, it's not like this, where round 7 is closer to the end, right? If it's an infinite number of bargaining rounds, every time you get to make an offer is like every other time you could have made the other offer, So therefore, you can kind of induct on this kind of like make a recursive relationship, right? So what am I going to do? What am I going to ask for now? Well, I can't give myself too much because then you'll reject me tomorrow. Okay, so but I still want a lot. Okay, so I want to choose the maximal offer which makes you want to accept it tomorrow. Well, what will that depend on? That'll depend on what you could get by making an offer tomorrow, right? But then you've got to think, oh, I can't make too stingy an offer because I got to make me happy the next time, right? But if we make it to that next time, then that situation is exactly the same situation I am in now. You see what I'm saying? And that's kind of how we did this. That's how we got this stuff here, right? Given that next time this is what I'll get, then this is what you would make, etc. Then this is what I will get. So assuming this is what this will result to me, right? But given that this and this are the same, then I just make this equal. Then that's how I can solve for it. So, have you ever seen this? It's sort of it's a simple principle. Have you seen? I'm sure you've seen this. Something like. Okay. Something like this. Say, but I have like 1 plus b squared plus b cubed. Okay, do you know what this is? Well, hopefully it also doesn't, it's bounded, so maybe b is less than 1. If b were 10, this is obviously, okay. So say b is less than 1. Okay, how do I solve this? It's the same kind of thing as this.
I think I've done something like this before, but
Okay, so one way to think about it is this. Well, it's a long infinite series, right? It says infinite sum. Let's just call it x. Okay. Then I can say, well, x is the same thing as 1 plus b times 1 plus b squared. Right? This is the same as this. I'm just factoring one of the b's out. Seem to. So what is this thing here?
oh,
X, right?
so what do you do? That makes sense.
So now I solve for it. So this is x minus bx. So what's going on? It's sort of the same. Well, not sort of. It is the same thing as this. Okay. it's a complicated thing, but I'm taking advantage of sort of recursive property to give you an equation, right? Just like a recursive property, right?
I learned this for the GRE now.
Yeah.
The GRE, that's where they taught us about it. They
Yeah,
said-
exactly.
The example was with the number 5,
Right.
and it was kind of crazy to understand how that changes.
Yeah, exactly, right. So, I mean, it seems, this is another, with math is so great, but it is a complicated thing. Like, you're never gonna solve this by using a computer, right? I mean, let's put this in R and figure it out. I mean, you could do that, but I mean, let's just actually use math and say, okay, well, you can compute it, but you don't have to because you realize this is recursive property. Whatever this number is, it satisfies this relationship. So once X satisfies the relationship, you can just solve for this. Similarly over here. Do you want a V2? No, I don't know how to solve for them X ante, right? But I can say, stipulate them, if I write them down, then I can realize they must be part of this kind of recursive relationship, and therefore I can solve. A lot of things in game theory like that, because a lot of things have this recursive character. It's sort of the same thing. Same spirit at least. Okay. All right. I think those are. I'll post the recordings, this one and then next ones too. Okay. I think I haven't posted last week's recording yet, but I'll do this.